So, good day everyone. This is the continuation sa report sa Group 3. Now, I am tasked to report about the Lambert Quadrilaterals. So, without further ado, let us start. So, Lambert Quadrilaterals. J.H. Lambert, or J.H. stand for Johann Heinrich Lambert, in 1728 to 1777, also attempted a proof of Euclid's fifth axiom using an indirect argument. So, J.H. Lambert or Johann Heinrich Lambert daw is nagtry siya nga i-prove ang fifth axiom ni Euclid using indirect argument. Then, Lambert approached the proof using a quadrilateral similar to the while I play next slide. So, in Lambert quadrilateral, ABEG, AB is perpendicular to BE, B is perpendicular to EG, and AB is perpendicular to AG. So, ang gigamit ni Lambert nga approach para ma-prove ang katong fifth axiom ni Euclid is what he called the quadrilateral. So, this is what we call the quadrilateral nga ginamino. Ang quadrilateral ABEG. Where AB is perpendicular daw siya sa BE. And then, BE, so this one, BE is perpendicular to EG, and AB is perpendicular to AG. So, muna siya ang ginapasabot sa itong quadrilateral. Lambert quadrilateral. So, Theorem 3.3.11, the fourth angle of Lambert quadrilateral is acute. So, as you can see here in figure 3.10, so, ang theorem 3.3.11 nag-state ng ikaupat daw nga angle sa Lambert quadrilateral is acute. Now, when we talk about acute, it is less than 90 degrees. So, as you can see, ang fourth angle diri is ang AGE. So, muna siya ang what we call the acute angle sa Lambert quadrilateral. So, next, the area of hyperbolic triangles. In Euclidean geometry, units of area are represented in terms of unit square. So, kung sa Euclidean geometry ta mag-matter, ang units area daw, gina-represent siya sa unit square. So, when talk about unit squares, katutong na ay mga square root, squared, no? Like, a squared, ingana. So, squares are used for this purpose for a number of reasons. So, ang squares daw is daghan siya purpose. For instance, they tessellate the plane and fill rectangular areas in a simple and direct manner. So, one usage sa squares daw or nganong helpful siya because it can fill rectangular areas in an easy way. Furthermore, there is a simple mathematical relationship between the linear dimensions of a square and its computed area. These and other features make the square a convenient shape for the unit of area in Euclidean space. However, since squares do not exist in hyperbolic space, hyperbolic area cannot be represented in terms of square units. So, some other representation is needed. So, since ang Euclidean space, diba, kaya nagagamit man sila og squares, no? So, it represents unit squares. But, sa hyperbolic space, squares do not exist. So, therefore, ang hyperbolic area niya is dili po siya ma-represent as square units. So, naay some other representation nga gihimo. So, in searching for a suitable unit of area for hyperbolic space, kay wala man siya, di man ta pwede magamit og unit squares, no? Kay wala may squares sa hyperbolic space. So, three formal considerations must be taken into account, in addition to matters of convenience. So, naay tulo ka formal considerations, no, nga gihimo. So, these considerations may be regarded as axioms of area. So, nato ginatawag nga axioms of area. So, tulo ka consideration. First is the area axiom 1. It states here that the area of any portion of the plane must be non-negative. So, dapat dili negative ang area sa portion, no? Muna siya ang state sa area axiom 1. Then, area axiom 2, the area of congruent portions of the plane must be the same. So, dapat ang area sa congruent ng mga portions dapat the same or dapat parehas, no? Then, muna siya ang sa axiom 2 or area axiom 2. Let's proceed with area axiom 3. So, the area of the union of these joint regions of the plane must be equal to the sum of the areas of the region. So, the area daw sa katong yun sa disjoint ka regions, to dapat equal siya atong sum sa area atong mga regions. So, area in the Euclidean plane may be defined as, so area in the Euclidean plane we can see it in figure 3.3.11. So, muna siya ang area sa Euclidean plane. So, na sila ano diri nga A is equal to, or area is equal to, this is also called the sum, no? Sum po na siya. Sum of R times D times R times D theta. So, in order to adapt this formula to the Poincare model of hyperbolic space, the shrinking ruler effect must be considered when this is done. So, the result is surprising because demonstrating that result is beyond the scope of this text, the following theorem is stated without proof. So, dapat mo-consider daw ang shrinking ruler. Kay, kung mabuhat to ni siya, no, ang result is kanang surprising or ma-surprise sa result. But, kanang pag-demonstrate sa result ani, no, is beyond the scope of this text man. So, natay mga following theorem, no, nga gigi-state, no, gigi-state. But, wala siya proof, no. So, this is one of the theorem, no, 3.3.11. The area of hyperbolic triangle with angle sum sigma is pi minus sigma, or sa degree, it is equal to 180 degree minus sigma. Then the most interesting aspect of this result is that area is measured in degrees or radians. And as a direct result of theorem 3.3.11, if two triangles have the same angle sum, they have the same area. So, sa 3.3.11 daw, pag ang duha daw ka triangles have the same angle sum, they have the same area. So, muna siya ang figure sa 3.3.11, no? Pag duha ka triangles, say for example, this one, duha na sila ka triangle, no? Kani, o kani. So, pag ang sum sa angle aning nga side is equal sa sum sa angle aning nga side, therefore, ang ilang area duha is equal po. Muna ang state sa theorem 3.3.12. So, in theorem 3.3.13, if two hyperbolic triangles have the same angle sum, they have the same area, no? So, sa theorem 3.3.13 na po is, pag ang duha ka hyperbolic triangles have the same angle sum, or na the same ang sum sa ilang angles, so, therefore, ang ilang pong area is the same po. So, finally, theorem 3.3.11 suggests that there is a largest triangle or class or largest triangles in hyperbolic space. Largest triangles have an angle sum of 0 and an area of 180 degrees. So, a triangle with its angle sum is shown in figure 3.12 and has shown here earlier. So, this is what we call the 3-ohm triangle. So, this figure is muna siya ang ginatawag na largest triangle sa hyperbolic space nga ang sum ani, so this is what we call the area of 3-ohm triangles. So ang sum daw ani, no, ang sum sa ilang angles is 0. So ang ilahang area po is 180 degrees. So muna siya ang gina-considered as largest triangle sa hyperbolic space. Now let's proceed, no, to summary. So, definitions in 3.3.1, the defect of hyperbolic triangle with angle sum sigma is pi minus sigma. Definitions 3.3.2, the distance between two parallel lines is measured along a common perpendicular between lines. So, when we talk about parallel lines, kat muna siyang lines nga wala nag-intersect, or this one example, yan. Muna siya ang parallel lines. So, ang duha ka parallel lines, ang distance, ang palayoon or ang kaduolon nila, no, sa duha ka parallel lines is ma-measured siya pinaagi, no, sa common perpendicular between atong mga lines. Then, let's proceed with the theorems. 3.3.1, the summit angles of Sacheri quadrilateral are acute. So, sa Sacheri quadrilateral, ang ilang summit angles daw are acute. When you talk about acute, it is less than 90 degree. Now, theorem 3.3.2, the angle sum of hyperbolic triangles is less than 180 degrees. So, ang angle sum daw sa hyperbolic triangles is dili siya mo exceed og 180 degree, but dapat less than 180 degree o mas baba sa 180 degree. Then, theorem 3.3.3, the sum of the acute angles of a right hyperbolic triangle is less than 90 degree. So, sum na po sa acute angles daw sa right hyperbolic triangle is less than 90 degree. So, since acute man siya, dapat less than gid ang iyahang sum sa 90 degree. Then 3.3.4, the sum of the interior angles of a convex hyperbolic polygon is less than the quantity of n minus 2 times 180 degrees. So, when you talk about convex hyperbolic polygon na po daw, dapat ang sum sa iyahang interior angles is di siya ma-exceed sa quantity of n minus 2 times 180 degree, but kanang baba lang siya, babaan na. Next, we have theorem 3.3.5. The angle sum of a Sachiri quadrilateral is less than 360 degrees. So, ang sum sa angle sa Sachiri quadrilateral is dapat less than lang siya 360 degree. Then 3.3.6, rectangles do not exist in hyperbolic space. So, let us always remember nga, when we talk about hyperbolic space, wala gid tayo rectangles nga makita. Then 3.3.7, in hyperbolic right triangle ABC, sides A, B, and C are opposite angles of A, B, and C respectively. Angle C is the right angle, then cos C is equal to cos A times cos B. So sa hyperbolic right triangle daw ABC, no, let us always remember nga ang right angle nato dira is ang angle C, and then cos C is equivalent to cos A times cos B. Then 3.3.8, parallel lines cannot have more than one common perpendicular. So, ang parallel lines daw is dapat wala siya daghan nga kaparehas nga perpendicular lines. 3.3.9, parallel lines are not everywhere equidistant. Then 3.3.10, intersecting lines cannot have a common perpendicular. So when we talk about intersecting lines, muna siya ang mga lines nga nag-meet, no? So dapat wala daw siya kaparehas nga perpendicular lines. Then 3.3.11, the fourth angle of a Lambert quadrilateral is acute as what I have explained earlier, no? Ang katong figure ngay ngani, no, muna siya ang Lambert quadrilateral. A, B, E, G. Ang ika-fourth angle niya is acute. So, less than 90 degree. Then, theorem 3.3.12, the area of a hyperbolic triangle with angle sum sigma is pi minus sigma or 180 degree minus sigma. Then, lastly, 3.3.13, if two hyperbolic triangles have the same angle sum, they have the same area. So, pag ang duha ka hyperbolic triangles na sila, ang sum sa angle nila is the same, so therefore, the same pud ang ilahang area. So, muna siyang pasabot sa 3.3.13. So, that would be all for our report. I hope you guys learned, and may God bless us all. Thank you.